and Assalamualaikum everyone. Now we are going to continue to discuss the MOSFET, focusing on the characteristics under non-equilibrium condition. We have discussed on MOS capacitor, and there are three behaviors of MOS capacitor, which are the accumulation, depletion, and inversion, and a conductive channel is formed at inversion state. We have seen that the gate voltage VGS controls the band bending in MOS capacitor that leads to the formation of channel. We can also draw energy barrier or EB diagram that shows that there are barriers at source and drain, and at equilibrium, the electrons from source cannot flow to the channel due to the energy barrier. So, in this subsection, our objectives are to understand qualitatively the mechanism of MOSFET behavior under bias and relate that to the current voltage characteristics. Since we know that the gate voltage VGS is important to form the channel, here I'm going to introduce the VGS for various MOSFET types. For enhancement type MOSFET, in equilibrium, the device is off. We need to apply VGS to turn the device on. At equilibrium, very weak channel exists due to band bending. For MOSFET, the current carriers are electrons. We need to apply positive VGS to bend the conduction band edge downward, to allow more electrons to flow into the channel to turn it on. For PFET, the current carriers are holes. We need to apply negative VGS to bend the conduction band edge upward, to allow more holes to flow into the channel to turn it on. For depletion MOSFET, in equilibrium, the device is always on. VGS must be applied to decrease the band bending, deplete the channel, remove the carriers, and turn off the device. For MOSFET, the current carriers are electrons. We need to apply negative VGS to repel the electrons in the channel and deplete the channel to turn the device off. For PFET, the current carriers are holes. We need to apply positive VGS to repel the holes in the channel and deplete the channel to turn it off. Now let's focus on MOSFET as the example. We consider the case when VGS is not 0 or varied, but VDS is 0. The above figure shows the connection when applying the gate voltage. When the positive gate voltage is applied, the channel energy is reduced since the channel is N-type. Under bias, the conduction band edge bends downwards towards the Fermi level. This makes the substrate surface at silicon dioxide and silicon is strongly N-type. Thus, more electrons in the channel and the conductance increased, resulting in a conductive channel being formed. Now let's take a look at the EB diagram. At equilibrium and below the threshold voltage, the barrier at the source and drain is very high, so only small amount of electrons at the channels. That makes the channel very low conductance. When positive VGS is applied, this will lower down the energy barrier between source and channel and thus allow more electrons into the channel. The higher the gate voltage, the barrier is lowered and the more electrons in the channel, thus the channel conductivity increases. Dependence of current to the applied voltage are represented in these two current voltage characteristics. The left one is transfer curve is taken by varying VGS and measuring IDS. During this measurement, VDS is 0. The threshold voltage VT can be determined from the transfer curve. The right one is the output characteristic, which is taken by varying both VGS and VDS and measure the IDS. We have discussed on the mechanism when we vary only VGS while VDS is 0. So now let's take a look on what is the mechanism when we vary VDS to further understand the output characteristic. When no VDS is applied, electrons in the channel do not drift. VDS is the same as the source voltage. Thus, there is no slope to the conduction band edge along the channel. When VDS is non-zero, the drain voltage is different from the source voltage. A longitudinal electric field exists in the channel, inducing current flow along the channel. When VDS is larger than 0, which is positive but still small, electron energy at the drain is lowered. Electrons that entered the channel from the source are accelerated towards the drain by the channel field, meaning that IDS flows from drain to source. The current that flows from drain to source depends on VDS, and the conductance of the channel depends on VGS. When no VDS is applied, electrons in the channel do not drift. VDS is the same as the source voltage, thus there is no slope to the conduction band edge along the channel. When VDS is non-zero, the drain voltage is different from the source voltage, a longitudinal. At very small values of VDS, IDS varies linearly with VDS. At larger values, the current levels off and saturates. When VDS is further increased, the slope changes faster at the drain end. However, at the source end, only small change in slope. Since current at one end of the channel must be the same as the current at the other end of the channel, the current IDS is limited to what can be supported by the source end. Currents do not flow in the gate terminal due to the insulating outside layer between the gate and the source, channel, and drain. We try to explain the current saturation with the lake analogy. Imagine we have two lakes, Lake S and Lake D. In between, we have a canal. The water is the carrier concentration that is controlled by the gate voltage, VGS. If VGS is very small, below threshold voltage, VT, the canal level is high. That separates the Lake S and Lake D, so no water can flow from Lake S to Lake D. Thus, no current flow below Vg equals to Vt, regardless of VDS. When VGS is large enough to reduce the barrier of the canal, water starts going into the canal, but still there is no movement of water because both lakes are at the same level. When you apply VDS, we have seen that the band diagram will bend, where the drain level moves downwards. Looking at this lake concept, when VDS increases, Lake D moves downward. The lower the Lake D go, more water from Lake S will flow into the Lake D. For MOSFET, if we increase VDS, IDS increase linearly. This is at 0.2 and 0.3. But when VDS is further increased, the slope changes faster at the drain end. However, at the source end, only small change in slope. From the lake analogy, after 0.3, even if Lake D goes lower, the amount of water that flow from Lake S to Lake D is still the same because the amount of water is limited by the amount of water at Lake S. From electrical point of view, current at one end of the channel must be the same as the current at the other end of the channel. Thus, the current IDS is limited to what can be supported by the source end. This is pointing to 0.3 and 0.4. The current does not flow into the gate terminal due to insulating outside layer between the gate and source, drain, and channel. Now let's compare the EB diagrams under VGS and VDS. VGS controls the barrier height EB at source and drain and the carrier concentration in the channel and thus the channel conductivity, while VDS controls the potential energy of the drain. The current flow in the channel, IDS, increases linearly with VDS, but at larger VDS, IDS saturates. Number of carriers available to carry current is controlled by EB, or actually by VGS, not by VDS. So increasing VGS can increase the saturation level of IDS. Let's take a look at the output characteristics. I've mentioned that during measurement, we vary VDS and VGS and measure the IDS. There are three regions of operation. At VGS smaller than VT, at this x-axis, this is the sub-threshold region, and here is the sublinear region where VDS is smaller than VD set, and saturation region where VDS is larger than VD set. VD set is the VDS value that marks the starting point when the current IDS starts to saturate, and ID set is the saturation current. For the sub-threshold region, the threshold voltage Vt is the minimum value of VGS required to form a channel that is sufficient to allow current flow between source and drain. VGS is smaller than Vt will result in ID equals to 0 or almost 0 regardless of VDS, which is the sub-threshold region. If VGS is larger than Vt and VDS is positive for N-type MOSFET, current can flow and the device enters the linear or saturation region. When the current saturates at one VGS value at ID set, increasing VGS will also result in increasing ID set. VDS controls the flow of carriers and the channel from source to drain. For VDS smaller than VD set, ID changes linearly with drain voltage. That is in the linear region, and for VDS is larger than V set, the current saturates. This is the saturation region. Finally, to summarize, we have discussed the mechanism of MOSFET under bias. There are two types of IV characteristics that were discussed, which are the transfer curve and output characteristics. VGS controls the formation of the channel and the carrier concentration in the channel. When we only vary VGS, where VDS equal to 0, and we measure IDS, we will get the transfer curve. Here, VT is the minimum VGS value to form the channel, meaning that at VGS smaller than VT, almost no current flow, and VGS larger than VT, the current flows. On the other hand, VDS controls the current flow in the channel. At low VDS, the current increases linearly, and at higher VDS, the IDS saturates. Varying both VDS and VGS and measuring IDS will give this output characteristic. There are three regions in output characteristics, which are subthreshold region, linear region, and saturation region.